Mrs. O'Loughlin here. We're going to look at data type conversion and type casting in this example. And so we'll look at a few of the slides first and do a couple of examples, and then I will get into some more nitty-gritty details, but try to give you just kind of the skinny version to start with, and then those of you that are interested will get into more details if you want. But when we work with operations, operations must be performed between operands of the same type. So, and the computer decides then if the operands don't match, then it's automatically going to convert one to be another type. That is called, well, we'll talk about what that's called in a minute. That could have a drastic result on calculations. We'll come back to this hierarchy of data types in a little bit, but when it's doing this, it's automatically doing what's called type coercion. So it automatically converts one operand to another data type. That's what happens when you use the CN operator. Remember that you bring in a character and it automatically converts it to an integer. Well, it converts or promotes if it converts to a higher type. So if I go back here, character wasn't on this list, but when it converts a character to an integer, the integer is the lowest type, okay? A demotion is converting to a lower type. So for example, I might take a double and try to make it an integer. That would be a lower type. And it's possible to do that in a couple of different ways. If I take an integer and cast it up, then I'm converting it to a higher type, okay? There are certain rules that are followed. It says character short, unsigned short are automatically promoted to integers. And that's what happens when you use the, again, when we use the CN operator. It takes a character and promotes it to an integer. When operating on values of different types, the lower ranked one is promoted to the higher one. And then when using the assignment operator, that's the single equals, the type of the expression on the right will be converted to the type of the variable on the left. Other rules, the demotion is required to use the assignment operator. Excuse me, if demotion is required, then the stored result might be incorrect. There's not enough space available. For example, if I try to take a floating point number or a double and assign it to an integer, it automatically truncates it. It chops it off. And so you have to be careful of that. Coercion also affects the value used in the calculation. It does not change the actual value assigned to a variable. And then we'll talk about typecasting, which is a way to get around some of those coercion rules, okay? When you need to temporarily change data to a certain data type. And that's the example we're going to start with. If we go to our online compiler, this is example 3.7 from your textbook 3-07 for the source code files, if you want to access that a little bit later. And in this example, it is bringing in two integer variables, books and months, and we have one double variable, books per month, which makes sense because that's a rate. And so we have some user input, and then it does some calculations. So I did an example, 13 books read in 3 months, so that's 4.33 books per month, which makes sense because it's a, when I take 13 divided by 3, I should get 4.33. Now, we're going to go back, and I'm going to do that same calculation. I'm going to copy this books per month, but we are not going to use the casting. Casting temporarily changes the data to an appropriate data type or a data type that we'd like to use. So if I take out this static underscore cast and I go ahead and do the same calculation, 13 books in 3 months, my answer is an integer. And remember, it's doing that because of integer division. Remember, integer division is going to just truncate off the decimal part. Well, that's not what we wanted, and so that's why this particular code uses the static cast. And so what it's doing is temporarily changing the value of books to a double, so then it will do double division, meaning this. And I remember when I take a double divided by an integer, then it yields a double, and that's part of that conversion. back in the slides, remember it said it's going to go to the higher one. If you have one of each type, then it will make it move up that hierarchy. So it's going to return a double if I have a double divided by an integer. And so that's what casting does. This is the format that you have to use when you're casting in C++. It's not like some of the other languages, and this is the current standard that is being used. Okay, so that is the skinny notes on doing conversions. Most of the time this is the one that you're going to see, but you can take a double and cast it to an integer if you want to use that temporarily. One of the reasons that you don't want to just maybe assign or change this data type, actually the most common way that you guys usually try to fix this is you make these other values doubles. But that might be completely inappropriate for your application because, for example, when you're counting how many books you read, you don't count a partial book. And so the data type that's best for books should be an integer. Now you could argue with me on the months. You could say, well, I could read a book in 1.5 months, and I might agree with you on that. But for the purpose of this example, they are saying that months and books must be integers. Books and months are integer values. And we don't want to change the integrity of that data, so therefore we don't want to change them to doubles just to get my program to work. I need to do this casting trick. Okay, next example is going to be example 3-8. This is example 3-8, and this one can kind of be a fun one. We'll talk a little bit about what some things you could do with this, but it creates a numeric variable 65 that's an integer, and it displays that number down here 65, but then it's going to use a cast to display the value of the converted number to a char data type. So it uses a static underscore cast char, and so it converts number to a character. And then notice it's in this cout statement, so then it outputs that. So if you notice, 65 outputs A. And that is because it's using what's called an ASCII chart. ASCII stands for American Symbolic Code for Information Interchange. And it is actually outdated now. But let's take a look at how they set this up to start with. And so if you take a look at these numbers here, this is an integer value. And what's on the left-hand side here is the associated character with it from the keyboard. So if I scroll down to 65, this is why it's giving me A. Capital A is 65 on the ASCII chart. And then if I keep scrolling down, I have capital letters, and then there's some of these funky symbols in between, and then there's lowercase letters. So this is how the computer knows how to alphabetize things, because it compares, for example, 65, if I have apple compared to banana, which one comes first in the alphabet is apple, because 65 is less than 66. Or likewise, if I do the lowercase, 97 is less than 98. And so it uses the ASCII code in order to put things in order, and it's also one way that you guys can kind of use or do some cryptography or some coding if you wanted to, because you could convert things, you can take numbers and you can convert them to words. I changed up the example just a little bit, and I assigned 3 integer numbers, 67, 65, and 84, and then I'm just going to output them. I want you to notice my cout statement. There is no semicolon at the end here because I'm using basically a run-on statement. And rather than having all of that code, I could have all the code on one line like this, but sometimes you will see code executed or brought down onto multiple lines like this. As long as it's readable, that's okay, but the end of the statement doesn't occur until the semicolon. So that's just showing you one other thing here. And so now, what is the mystery word that's going to be printed? Well, if I execute this, we see that it prints the word cat. And that makes sense because capital A was 65, so then capital, if I go 65 for A, 66 for B, 67 for C, etc. And so you could actually use this in order to do some cryptography, because you can shift the letters now. You can take an integer. What happens if I want to print, 84 minus, and I have a shift value, for example. If I want to take all of them and assign a shift value. So let's say I have my shift value this is what's called a Caesar cipher, if I shift it by a certain amount. And so I could take each of these letters then and assign a shift value to it, so to speak. And then all of a sudden my word cat, now this is going to be interesting. I don't know what it's going to do when it goes to the 67 minus 4, because that's, or 65 minus 4, because that's going to be before the letter A. So let's see what it does. So it gets question mark equals and P. So now I just created a mystery for, my cat. If I want to change it back, instead of subtracting the shift, I can then add the shift and I'll get back to the original. And so that's called a Caesar cipher. So just a little bit of cryptography there. That is the end of this introductory video. I am going to do another one that's going to talk a little bit more in detail about some of the slides, specifically the slides that talk about this hierarchy of data here, and we'll talk about that on a different one. But you don't need to listen to that unless you are interested in learning about figuring out the size of these and how they are related.